Hello everybody. In this video we're going to review discrete random variables. Problem number 1. Using historical records, the personnel manager of a plant has determined the probability of X, the number of employees absent per day, is given in the chart below. So according to this chart, we're going to calculate the probability that X is between 2 and 5 inclusive, X is greater than 5, and X is less than 4. Our chart is already given in probabilities, and X is a random variable that is representing the number of employees absent per day. So probability that X is between 2 and 5 inclusive 2 and 5 is equal to probability that X is equal to 2 plus probability that X is equal to 3, X is equal to 4, and X is equal to 5. And if we can substitute the values from the chart given, we can obtain the probability that X is between 2 and 5. Here in this chart, probability that X is 2 is 0.3092 plus 0.3397 plus 0.22 plus 0.0794, and if we add them up all, we obtain 0.9483. So this is the probability that X is between 2 and 5. Now we're going to calculate the probability that X is greater than 5. 5 is not inclusive. That is equal to probability that X is equal to 6 plus X is equal to 7 given in the table. So here probability that X is 6 is 0.18 and probability that X is equal to 7 is 0.0046, and if we add them up we obtain 0.0226. Now we're going to calculate the probability that X is less than 4. So the logic is the same. It is equal to probability that X is equal to 0, X is equal to 1, X is equal to 2, X is equal to 3, but not 4 because 4 is not inclusive here, because it is strictly less than 4. And if we substitute the probability that X is 0 is 0.0043 plus 0.0248 plus 0.3092 plus 0.3397, and if we add them up all, we obtain 0.678. So this is the probability that X is less than 4 strictly. Problem number 2. The probability that a university graduate will be offered no job within a month of graduation is estimated to be 6%. The probability of receiving 1, 2, and 3 job offers has similarly been estimated to be 38%, 32%, and 24% respectively. Determine the following probabilities. This problem is similar to the problem number 1, so we can table very fast. Let's table it. And in this table, 0 job offered, 1 job offered, 2 jobs offered, and 3 jobs offered. And probability that 0 job offered is 6%, which is 0.06, and 1 job offered is 38%, 2 jobs offered is 32%, and 3 jobs offered is 24%. Here in A, we are going to calculate the probability a graduate is offered fewer than 2 jobs. Offered fewer than 2 jobs is the sum of 0 and 1. So this is equal to probability that 0 job offered plus 1 job offered, which is 0.06 plus 0.38, which is 0.44. And in part B, we're going to calculate the probability that a graduate is offered more than one job. More than one job offered is here, probability of 2 and 3. So that is equal to probability of 1 plus probability of 2, which is going to be 0.32 plus 0.24. As long as you can table it and tell all the probabilities, the rest is addition. And this is going to be 0.56. This is the answer. This is the answer. Problem number 3. A survey asks adults to report their marital status. Suppose that in the city which the survey is conducted, 45% of adults are married, 11% are single, 22% are divorced, and 22% are widowed. Find the probabilities of each of the following events. Before we do that, let's table everything. So we have married, single, divorced, and widowed. According to survey, 45% are married, 11% are single, 22% are divorced, and 22% are widowed. And some of them has to be 1. Okay, now we're going to find the adult single. So it's already told here in the survey, because out of 100 people, 11 people are single. So the answer here is 11%, which is 0.11. The adult is not divorced. Adult is not divorced is all of them but divorced. So this excluding divorced, all of them but divorced. So it's going to be 0.45 plus 0.11 plus 0.22. It's going to be 0.78. 0.78. The adult is either widowed or divorced. Either widowed or divorced is this set. So we're going to add them up, which is 0.44. Problem number 4. Events that are complementary must also be mutually exclusive. This is true because complementary events must also be mutually exclusive events. Two things cannot happen at the same time. The event and the complementary of the event cannot happen at the same time. For example, you can't go to school and you go to school at the same time. I am at home and complementary I am not at home. These two things cannot happen at the same time. So it is mutually exclusive. So the correct answer is true, which means event and the complementary is also mutually exclusive. Problem number 5. Suppose that a single die with 25 sides, numbered 1 through 25, is rolled once. What is the probability of getting an even number? Here, our sample space is the numbers from 1 through 25. And we know that the size of the sample space is 25, because we have 25 numbers here. And our event is the probability of getting an even number, starting from 2, 4, up to 24. And here the size of the event is 12. 24 divided by 2 is 12, or you can count out. And probability that even numbers, which is our event, is equal to size of event over size of sample space, which is 12 over 25. So 12 over 25, or 0.48, is the correct answer. Problem number 6. An electrical system consists of two components in series, as indicated in the diagram. Both components must work for the system to work. During a day, let F1 be the event that component 1 fails, and F2 be the event that component 2 fails. So we're going to find the event the system fails during a day, the event the system works throughout the day. So I made a diagram for you guys here, and we're going to make the chart together. So F1 itself is the event 1 which the component fails. Let negative sign represent that. So this is our F1. And F2 likewise is the system fails, and let negative sign represents that. And we were given that both components must work together for the system to work. So these two guys are not working already. Fail, fail. So system is already fail. Let F1 fail and F2 not fail. So this is F2 complement. But still the system fails because they have to work together. Let F1 pass, which is F1 complement. Let F2 fail, which is negative. System still fails. Let F1 complement, which is going to be pass plus, and let F2 complement, which is plus, then the system pass. So this is the only condition that the system passes. F1 complement union F2 complement. In problem 1, they are asking the event that the system fails. So here F1 union F2 is already the answer because they are already fail, fail, and the union of two fails is still fail. So we don't even need to check the others and go to details. Because the definition of F1 and F2 is given as fail, their union is already fail. The event the system works throughout the day is only this condition, which is F1 complement union F2 complement. That's it. So it seems this, but it is not. Here the trick is this. It's going to be F1 complement intersect F2 complement, because this is not meeting to two conditions. Our second condition is both components must work together. In B here, which is the correct answer, both conditions are working, because F1 complement intersect F2 complement is the condition that they work together, and F1 complement is plus, F2 complement is plus, so the system is plus. But here the trick is F1 complement union F2 complement is union, by definition, is F1 complement plus F2 complement minus their intersection. So here this is the biggest distractor in this question. So the answer B and answer B is correct. Problem number 7. Helen is considering buying a new car. The set of cars she is considering is shown via the Venn diagram below. Within this set, the set A contains cars made by Toyota, the set B contains cars that are blue, and the set C contains cars that have a manual gearbox. The subsets A, B, C, D, E, F, and G are defined by the boundaries in which they are located in the diagram here. So according to this Venn diagram, we're going to find Toyota cars that are not blue. So let's write out A is the Toyota cars, so this is the set for Toyota cars. Toyota. And this is the blue cars, and this is the manual gearbox cars. So Toyota cars that are not blue. So Toyota cars are A, B, E, F. Out of these cars, A and F are not blue, B and E are blue. So A union B is non-blue Toyota cars. Part B, cars that are neither Toyotas nor have a manual gearbox. So we don't want Toyotas, we don't want manual gearboxes, and the rest is C here. We have C already, but we have bigger definition here. A naught intersect B naught intersect D naught intersect E naught intersect F naught intersect G naught is giving us C here actually. And C itself is just blue cars, but not indicated whether Toyota or not. Here exact definition is asking for neither Toyotas nor have a manual gearbox. So this is the most general definition that indicates C. Here A naught is everything else but A. B naught is everything else but B. So the common intersection of all descriptions A naught, B naught, D naught is this C. So that means this is C. So here the answer is B again. Part C. Blue Toyota cars with manual gearbox. So blue Toyota cars are only B and E, and out of B and E, only E has the manual gearbox. So this is the answer. Problem number 8. The players on a soccer team wear shirts, with each player having one of the numbers 1 through 11 on their backs. The set A contains players with even numbers on their shirts. The set B comprises players wearing an odd numbers less than 7. The set C contains the defenders, which are those wearing numbers less than 6. Select the correct set that corresponds to each of the following. Let's make the Venn diagram. So here set A contains the numbers less than 11 and all even numbers. So 2, 4, 6, 8, 10. Set B are the numbers, odd numbers less than 7, which is 1, 3, 5. And set C are the numbers less than 6, which is 1, 2, 3, 4, and 5. 6 is not inclusive, and here 7 is not inclusive. Now let's merge the common numbers. So we have 1 here, so we can write it B intersect C. Likewise 3 and 5 are the common numbers. So here 2 and 4 are the common numbers, so we can write them here. If we rewrite better, 2 and 4 are here, 1, 3, 5 are here, nothing is here, nothing is here, and 6, 8, and 10 are here. Now we can answer our question. A intersect B union A intersect C. A intersect B is 0, empty set, and A intersect C is 2 and 4, and union of that is 2 and 4. So here the answer is 2 and 4. A intersect B union C. B union C is 2, 4, 1, 3, 5. And if I intersect this with A, again I get 2 and 4. As long as you make the correct Venn diagram, all you have to do is just follow the instructions here. So you can find B union C and intersect it with A. You can find A intersect C, A intersect B separately, and take the union. Problem number 9. Determine the size of the sample space that corresponds to the experiment of tossing a coin the following numbers of times. So we're tossing the coin 3 times. Our sample space omega will consist of 3 of them can come head, head, head. We can have head, head, tails, such that tail, tail, tail. So we have 2 options, head or tail. And we're tossing the coin 3 times. So it's going to be 2 to the 3rd, which is 8 times. So the number of the subsets, which is the size of the omega, which is the sample space, is 2 to the 3rd. Number of tossing on the exponent, and we have 2 options, head or tails, on the base. So similarly, this is going to be 2 to the 4th, and this is going to be 2 to the n. 2 to the third, 2 to the fourth, and 2 to the n. Problem number 10. A die is rolled. Find the probability of the given event. So the number showing is a 4. Our sample space rolling a die is 1, 2, 3, 4, 5, and 6. And the size of omega is 6. Here our event on part A is 4. And the size of event here is 1. And probability to obtain 4 is the size of event over size of omega, which is 1/6. So this is going to be 1 over 6. The number showing an even number. Even numbers are 2, 4, and 6. So we have 3 such numbers. 3 over 6 will be 1/2. The number showing is greater than 4 is only 5 and 6, which is 2 size 2 event, 2 over 6, which is 1/3. Problem number 11. A ball is drawn randomly from a jar that contains 7 red balls, 7 white balls, and 8 yellow balls. Find the probability of the given event. So our sample space omega has 7 plus 7 plus 8, 22 balls. And out of these 22 balls, 7 of them are red, so 7 over 22 is the probability of picking red balls. Likewise, white balls are 7, so 7 over 22 is the probability of picking white balls. And yellow balls are 8, so 8 over 22, which is 4 over 11, is the probability of picking yellow balls. Problem number 12. One die is rolled. Let event A be die comes up even numbers. Event B die comes up odd numbers. Event C die comes up to 4 or more. Event D die comes up to at most 2, and event E die comes up 3. So we're going to answer whether they are mutually exclusive or not. The events are mutually exclusive if they cannot occur at the same time. So if they cannot occur at the same time, they are mutually exclusive. So let's write out the events. Event A is the die comes up even numbers. So 2, 4, and 6. Event B is odd numbers. Event C is the die comes up 4 or more, which is 4, 5, and 6. Event D comes up at most 2, which is 1 and 2. And event E is that die comes only 3. Let's check one by one. Are events C and D mutually exclusive? C and D is here, and they don't have any common number, so yes, they are mutually exclusive. C and E, we compare 4, 5, 6, and 3. Yes, there is no common number. Are events A and C? A is 2, 4, 6, and C is 4, 5, 6. So 4 and 6 is already common. At least one common is violating the mutually exclusive, so this is no. Are events A and B? Yes, odd numbers and even numbers cannot come at the same time, so they are mutually exclusive. Are event B and C? B is 1, 3, 5, C is 4, 5, 6, 5 is common, that is violating, so not mutually exclusive. Problem number 13. Determine whether the following number can possibly be probability. Write yes for yes and no for no without quotations. 0, yes, 0 is the probability. Anything can be 0%. Let's use green. 1 is probability, a possible probability. Anything can happen 100%. Negative 3 is not probability measurement because probability cannot be negative. Probability has to be a number between 0 and 1. 3.9 cannot be a probability because it is a number greater than 1. 1/2 is probability, it is less than 1 and greater than 0. And likewise 0.1 is probability. Problem number 14. 3 contractors, call them A, B, and C, bid on a project to build an addition to some place. Suppose that you believe that contractor A is 2 times more likely to win than contractor B, who in turn is 7 times more likely to win than contractor C. What are each of their probabilities of winning? So we have contractor A, contractor B, and contractor C. Say contractor C has the X amount of probability. We know that B has 7 times more likely to win, and A has 2 times more likely to win than B, which is 14x. We know that the total probability has to be equal to 1. So 22x is equal to 1, so x is 1 over 22. So contractor C is 1 over 22, contractor B is 7 over 22, and contractor A has 14 over 22 chance to win the bid. Problem number 15. 4 candidates are running for mayor. The 4 candidates are Adams, Brown, Collins, and Dalton. Employing the subjective approach, a political scientist has assigned the following probabilities. Determine the probabilities of the following events. The event that Adam loses is the event that anybody else is winning but Adams. So it is 0.1, 0.2 plus 0.14 is winning, which is 44%. That means Adam is losing. Either Brown or Dalton wins. Brown or Dalton wins is 0.1, 0.10 plus 0.14, which is 0.24. Either Adams, Brown, or Collins wins, which is Adam 0.56, Brown 0.1, and Collins 0.2, which is 6, 1, 6, 7, 8. So 0.86. Problem number 16. The probability that a certain horse will win the Kentucky Derby is 1/5. What is the probability that it will lose the race? The total probability is 1. So 1 minus 1/5 will be the probability that it will lose the race. So you can express 1 as 5 over 5 minus 1/5 is 4/5. So 4/5 is the probability that the horse will lose, 1/5 will win. And if you add them up, the probability has to be 100%, which is 1. So this is the complementary of 1/5. Problem number 17. Events A and B are mutually exclusive. Probability of A is 0.4 and probability of B is 0.6. Find A union B, the probability of A union B, to 1 decimal place. Since they are mutually exclusive, their intersection is empty set, and union by definition is probability of A plus probability of B minus A intersect B, and we know that A intersect B is 0 because they are mutually exclusive. They don't have anything common. So probability A plus probability B will give us the union. 0.4 plus 0.6 is equal to 1.0. 1.0 because they're asking one decimal place. Problem number 18. If A and B are mutually exclusive events with probability of A is 0.35 and probability of B is 0.55, find the following probabilities. Let's make Venn diagram before we start. We were given that probability of A is 35%, probability of B is 55%. We know that they are mutually exclusive, so their intersection is the empty set, but the total probability has to be 1. 0.55 plus 0.35 is 0.9, so we have to add 0.1 outside of event A and outside of event B, which is the total sample space, which is omega, is the 100%. So probability of A intersect B is 0% because they are mutually exclusive. Probability of A union B is the sum of 0.35 and 0.55, which is 0.9, 90%. Probability of A not is whatever is not A. So it is 55 plus 0.1, which is 0.65%. A union B not. A union B not is 0.1. We forgot B not. B not is 0.35 plus 0.1, which is 0.45. And A intersect B not. B not is everything else here. And A is here. And B not intersect A is A, which is 0.35%. Problem number 19. What is the probability that a positive integer m in the range 1 through 100, which is selected randomly, is divisible by 3? So we are looking for the numbers which is divisible by 3, 1 to 100. So they are 3, 6, 9, 99. So the size of event is 33 because if you divide 100 by 3, you obtain 33. 1 is the remainder, it's not important. So we have 33 numbers that are divisible by 3. So the probability is 33 over 100 because the size of the omega is 100. So 33 over 100. Problem number 20. Suppose a couple plan to have 3 children. Let X be the number of the girls the couple has. List all possible arrangements of girls and boys. For example, if the couple had 2 girls and then a boy, then type girl, girl, boy. Separate each item in your list with a comma. Okay, so let's list the combinations that they can have. They can have boy, boy, boy in this order. They can have boy, boy, girl, boy, girl, boy, girl, boy, boy. They can have boy, girl, girl. They can have girl, boy, girl. And they can have girl, girl, boy. And they can have 3 girls. So we have to have totally 8. 1, 2, 3, 4, 5, 6, 7, 8, because we have 2 options, either boy or girl, and they would like to have 3 children, so 2 to the 3rd is the 8. That's the total number of the subsets that they can have. So this is the combination. So you have to write here boy, 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 comma, everything else here, and finally girl, girl, girl. List the sample space for X. So X is representing the number of the girls, so the couple can have 0 girl, as in example 1. Couple might have 1 girl, as in here and here. Couple might have 2 girls, so X can take the value of 2. Or the couple can take maximum 3 girls, so X can take maximum 3, minimum 0. So 0, 1, 2, and 3. Probability that X is 2 means 2 girls. So this event and this event are the 2 girls, and 3 out of 8 is the value that X can take 2. Find the probability that couple have 3 boys is only this, so it's 1/8. That's it for discrete random variables. See you at the next probability topic.